बिस्मिल्लाहिर्रहमानिर्रहीम। अस्सलाम वालेकुम डियर स्टूडेंट्स, कैसे हैं आप लोग? Okay, so in previous lecture we have discussed the AC radiating meter. So let's just go through take a review. So we started from uh, rectifier, half wave rectifier based meters, and this was the first diode half wave rectifier we have discussed. Then we move on to full wave rectifier. This is one of the improved diode rectifier because in negative cycle the diode D2 conducts, and therefore the leakage current because of negative cycle in D1 that does not affect the reading of meter. In both cycles, D1 and D2, they conduct positive and negative cycle. We have bridge type full wave rectifier, and we have seen the voltmeters. And the other one is half bridge but full wave rectifier. In this case, we have only two diodes, but their configuration is such that we have basically replaced the uh, other two, D3 and D4. We have replaced them with resistance with the same amount of resistance. And the midpoints of these two, we connect a meter over there along with some resistances to limit the current going through the meter. Then we find out sensitivity of the circuit ohms per volt. So if the resistance of meter is too high per volt, then meter is called as sensitivity is high for that meter. Similarly, all these meters, they are basically tuned uh, to have a single type of waveform, that is maybe we tune it for sinusoidal waveform, and to measure other types of waveform and their uh, signals. For the measurement, we have to uh, use some tuning factor or correction factor if the waveforms they change from sinusoidal to non-sinusoidal waveforms. Then you just multiply the meter reading with this factor and get the correct value for the certain waveform. Then we discussed iron vein meter. In this basically we have on the single coil, and uh, each uh, side stationary coil and the moving vane, they have a flat metallic strip, which is basically used to get the magnetized. When it is magnetized, the same sides, north and north, they repel each other, and therefore, due to the repulsion of this metallic strip, the pointer uh, is changed from 0 to onward to get a proper reading. Then we discuss the thermocouple meter. In this case, we have basically two different types of materials, and they have mm, uh, uh, two different types of material. When they are heated, they get they get voltage drop across it. Similarly, on the hot side and on the cold side. So, in this thermocouple meter, we have basically heat element, a resistive element, which consumes the current and gets heated, and the thermocouple, when is joined with that uh, element, then it get voltage because of the temperature change, and meter gets the reading of the voltage. Similarly, we have electrostatic meters, and they work on basically capacitive effect. It's attracted this electrometer. In this case, there are basically two half or semicircle plates, in which one is a fixed plate and the other one is moving along with the pointer. When voltage is applied to the to both moving plate and fixed plate, there is a distance between these two plates, and uh, due to that distance, a magnetic field is produced between these two, and which attracts the each other. The moving plate, it gets adjusted according to the, or gets attracted due to the magnetic field, and therefore the pointer moves to indicate the magnitude of the input signal. Then we discussed the electrodynamometer, and in this electrodynamometer we have basically two portions. One is the moving portion, which has a pointer in it, and its core is uh, has an electromagnetic coil, and therefore it is named as moving coil. Whereas the stationary part, where we require magnetic field, this magnetic field is also developed by the electromagnetic coil. So one core is on the left side and other one is on the right side. So both cores, their coils, they are connected in series, and ultimately they are also going to connect with the moving coil. So depending upon the connection type, we get it whether for voltage or current. So if the moving coil and the fixed coils, they are connected in series, we get a voltmeter. And if the fixed coil, which is also known as current coil, is connected in series with moving coil in such a way that there is a safety parameter also. A shunt resistance is connected in parallel with the moving coil, and the total current which passes through the current coil is basically divided in moving coil resistance and shunt resistance, and therefore we have the reading of the current. Then using the both configurations, we can use the dynamometer to measure the power consumed by the load. The power measurement of a single phase or a three phase, depending on the requirement. So current coil and the potential coil, they are connected in such a way that first we have a current coil and then we have potential coil in parallel with the load, and both equivalent resistance they are in series with the current coil. So in series with the moving coil there is a swamping resistance, and that is to mitigate the effect of heat produced by the current uh, carrying coil of potential coil. So basically, when current passes through both coils, and because these two coils, one is the fixed one and potential coil, can be moving, so therefore, due to the same amount of current, but in different coils, the torque is produced, and therefore pointer moves to indicate the deflection of the power. So then there is a difference depending upon the high current, high load side, or low current, low load side. So if the current is high, then with the power line, in first current coil is connected, and then in parallel we have a potential coil parallel with the load. But if the current is low, then we first connect the potential coil in parallel with the power line, and then we have current coil in series with the load, so that smaller currents can be measured with some accuracy. Then we have discussed that because of the two currents flowing in the, actually three currents, but load current is what we want to measure, and the other two currents are the total current and the moving coil or potential coil current. So because of these two currents, the actual reading uh, is for the total current basically increased a little bit, and therefore because of that the magnetic flux is going to rise, and therefore there is a chance that pointer gets higher torque and it reads a little higher value. So to compensate that, the potential coil is wounded along with the current coil in such a way that the current direction that flows in the potential coil, which is wounded on on the fixed stationary core gets the reverse current, gets the current direction opposite to whatever is the total current flowing in the current coil, and therefore the this compensation or this modification will maintain the flux equal to the load flux, and by reversing the current we will produce a reverse current which will develop a flux opposite to the total flux, and therefore the equivalent flux would be equal to the load flux, and therefore the torque developed would be uh, equivalent to the load current. Therefore, this compensation is necessary to get the accurate measurement out of the wattmeter. Then we have Hall effect wattmeter. So what is Hall effect? When a metal which is carrying some current is placed in a magnetic field, it gets a voltage produced perpendicular to the current direction. So this is basically the configuration of Hall effect wattmeter. So in this case, what we are doing is basically the line uh, is gets the current, and that current passes through the core of the stationary uh, piece or stationary core, and develops a magnetic field in the air gap of the core where we have placed Hall effect sensor, and the current that flows through the Hall effect sensor is basically uh, due to the parallel connection. So this is basically the moving coil. So therefore we have a potential across the Hall effect sensor, and there is a resistor that controls the current of the moving coil meter, like controls the current that should flow from the Hall effect sensor. So therefore, the potential which is applied to the Hall effect gives us the value of voltage that is in the line, and the magnetic field that is produced according to the line current. So therefore, we get the voltage out of the Hall effect sensor. We get the voltage out of Hall effect sensor, and that voltage is used to measure the uh, power of the wattmeter, of the line current and the voltage. Similarly, we can use the power meter, the wattmeter, to measure the multi-phase power, like a three-phase. So in three-phase, basically we are going to use two dynamometers or two wattmeters. So in this case, basically we have two wattmeters connected in series of the phase 1 and phase 2, whereas the potential coil that on one side is connected after the current coil, and the second terminal combined with the second wattmeter connected to the phase of the third uh, phase. And then after that, we have Y connected load, and we consider the balance load. So all the resistance, for example, they are equal, and therefore the current passing through the load is equal in all the phases. So therefore, depending upon the resistance, there is going to be have a power factor. So if low resistance is there, so there is zero power, unity power factor. So therefore, the reading of wattmeter 1 and wattmeter 2, they are going to be equal. But in case of RL load or RC load or load with a power factor, then the reading of P wattmeter 1 and wattmeter 2, they are going to be different. So if the power factor is less than 0.5, then we can we can take a difference between P1 and P2 or wattmeter reading of wattmeter 1 and wattmeter 2. Whereas if the power factor is higher than 0.5, then we are going to add the powers P1 and P2. And similarly, there is possibility that we have only inductor or pure capacitor is connected. So only reactive load, then the P for power reading of the wattmeter 1 and wattmeter 2, they are going to be equal but opposite in the polarity. So in case of inductor, either P1 is equal to negative of P2 or vice versa. P2 is equal to minus P1 depending upon the type of reactive load. Then we also have another configuration for four-wire system in which the load may not be a balanced load. So in this case, I must draw the load, how the load is going to be connected. So here we have one resistance, second and third, and their neutral points, they are connected to the fourth wire. So therefore, if we have unbalanced load, then in this case, the neutral line will have a non-zero current. That means a very a small amount maybe of current is flowing in the neutral line as well if the load is unbalanced. So in this unbalanced case, we have to use 3 wattmeters. So wattmeter 1, 2, and 3, they are going to give us the values of each phase, voltage, and current. So they are going to give us the different powers. So therefore, we can do the same by if the power is if the load is balanced, and purely resistive load. Then we have P1, P2, and P3 all equal to each other. But in case of unbalanced load, each wattmeter is going to give us the different reading of the power meter. Similarly, we also have a power factor meter, which basically gives the difference between the voltage and the current. And this is the construction of a single phase have quadrature coil, and it can measure the power factor. So how that is done? We have current coil, again core which has a wounded coil, but that core is fixed. And then we have two potential coils. Instead of single potential coil, we have basically two moving coils. So the core of these two moving coils is basically perpendicular to each other, and we have make sure that remains perpendicular because one potential coil is connected with the inductor and the other is connected with the resistance. So therefore, the current flow and accordingly the torque produced in the potential coil core will maintain a 90-degree phase phase difference. And then when we have a current of a load current which is the load has the power factor, and according to that the current which is going to be divided in potential coil and the load current that would get affected by the angle that has a load of the power factor of the load. So the angle between the voltage and current that is going to play in this scenario, and the potential coil, quadrature potential coil, is going to give us that indication. So this is basically induction type power factor meter in which you can see we have multiple types of coils. The current coil, then we have moving vane, and with the moving vane we have three-phase potential coils also connected, so with which we are going to connect the power line. Similarly, power factor can be measured by using two wattmeters. In this case, again, the same we have discussed earlier. Because of two wattmeters, there are going to be have a low power and high power readings, so we can take the difference and get the total power and power factor. Similarly, we may have a reactive power meter, and then we discuss the uh, energy meters based on the induction process. So basically, this induction meter uh, is based on the magnetic field and the metallic plate interaction, because when a metallic plate is placed in the magnetic fields, it is going to get eddy currents, and those eddy currents will make this plate movable. And when the plate is moved or rotated, then there is a gear mechanism and numbers, rotating numbers attached to that, and each rotation gives the units. Like here, uh, so each rotation moves one of the numbers. The last one, which is basically the units in watts, and depending upon the rotation which is calibrated, for example, maybe 340 rotations, they they result in 1 kilowatt hour. So therefore, the load, depending upon the load power, if that power is consumed 1 kilowatt per hour, then there are going to be 340 rotations in the metallic disc. Similarly, if the power is going to be half, therefore the rotations are going to be half in an hour. So therefore, depending upon the load, the disk is going to rotate, and these are the numbers. So when unit circle is completed, it completes the circle from 9 to again 0. Then 110 is moved. Similarly, when 10 completes its rotation to 9, then after that the 100 circle change to one position. And similarly, when 100 is completes its circle, then 1,000 cycle moves one unit. Uh, then we have other instruments also, like a transformer, which can be used as an instrument. And we have two types of transformers, one for potential measurement and also called PT, potential transformer. It basically steps down the high voltage to the low voltage secondary side, so that we can have a proper measurement. Similarly, we have a current transformer, also known as CT, and that is going to be connected in series with the line, and the secondary of that transformer again going to have some voltage on the other side, and we can measure the voltage, but gives us the value of current. And then we have some special kind of current meter called clamp on meter. And in this, we have basically core divided into two halves, and with the help of a button, we can separate the two cores. And when the button is released, we can hang it on or clamp it on a current carrying wire or conductor. So this core has a secondary winding, and therefore the current carrying conductor will produce some magnetic field, fixed magnetic field, uh, and the core is going to detect that magnetic field and ultimately the secondary coil is going to get some voltage due to that magnetic field. And basically this magnetic field is going to be uh, sinusoidal type, for example. So therefore, we need a rectifier to get the DC value in the meter. So that is it. We just wanted to have a review because the chapter is a little longer than the previous ones. So we just had an overview of this chapter. Then in next class we are going to start the next chapter, which is chapter 7. Ji, regarding this chapter, if you have any questions.